Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about the centrifuge. First, let us understand what a centrifuge is, what is its working principle, and what are its types, and such things. A centrifuge works on the principle of sedimentation. As you know, the sedimentation is a process by which the solid particles suspended in a liquid, they settle down at the bottom of the tank in which that content is retained. So basically, the solid particles which are suspended, gravitational force act on them and they settle down. And the gravitational force, they are counteracted by the buoyancy force and the drag force, and the resultant force that is acting upon it, that decides the acceleration of that particle that goes down. And if the acceleration is zero, then it reaches the terminal velocity, and all those basic theory are there in the normal textbook. You can go and refer them. Now, the most important part is the gravitational force of attraction. That means if this is the particle that is suspended in the liquid, then mg is the gravitational force of attraction, where m is the mass of that particle and g is the acceleration due to gravity. Now, acceleration due to gravity is same, it is 9.81 meter per second square. But mass is different for different particles. Now, if mass is very high, then mg will also be very high. In that case, the settling will also be fast. But if mass is very small, that means if the particle size is very small, or its density of the solid particle, it is very close to the liquid in which it is suspended. In that kind of situation, the mg will be very low, and there will be difficulty in settling, or the settling rate will be very low. Now, if we can create a situation whereby the force of attraction due to which the settling occurs, that increases manifold, then the settling rate will also be very high. Now, centrifuge is the device which creates that situation. In centrifuge, that entire content, that is the solids suspended in the liquid, that is rotated with a very high speed, high angular speed, maybe of the order of, say, 5,000 or 10,000 RPM, or even more, 15, 20,000 RPM. So when the suspension is rotated in such a high angular speed, then huge centrifugal force acts on that particle, and as a result of that, it goes outward, and the lighter molecules, that is the liquid molecules, that goes inwards. As a result, the solid material and the liquid material, they distinctly separate from each other. So that's exactly what centrifuge does. Now we will go into the detail of how it works. I will show a few diagrams and some animations so that you can understand it better. For that, let us first go to the Aspen simulation window and see where we can get this centrifuge block. So this is the Aspen Plus simulation window. You will find the centrifuge in the model palette. You have to go to the solid separator. So it will be over here. So this is the centrifuge. Okay. So what you need to do, you need to bring it over here, and you will find this is a feed, compulsory feed, red color, and this is the liquid outlet, and this is the solid outlet. So you have one compulsory feed and two compulsory outlet. One liquid outlet, one solid outlet. Okay, so there are optional extra outlets where you can give. Suppose if you have two immiscible liquids, then you can separate them with this centrifuge operation, and you can earmark the outlet for individual liquids. First, let us rename them. So this is feed, this is liquid, and this is solid. Okay. Now first go to the block and see what are the inputs that we need to specify. Now this is the centrifuge model. You have to first give the model specification. Now here you will find that there are 5 types of model specifications that you can mention. One is solid separator. Now the solid separator you have already learned. I mean, there is nothing more to discuss about it. You have to specify the phase separation, fraction of solids to solid outlet, or fraction of liquid to liquid outlet, or liquid load of solid outlet, etc. So based on which one you use, that particular parameter will be open for you. So suppose if you use this will be off and this will be on. So you can use the centrifuge as simple solid separator. So you are not basically using the principle of centrifuge over here. It is just a solid separator, plain and simple algebraic calculation. But other 4, that is perforated basket, decanter, disc, and pusher, these are the types of centrifuge that are available in the industrial operation. So we shall learn each one of them, how they operate. At the end, we can solve an example problem that involves all of them. Okay. Now first, let us understand what is perforated basket. The moment you choose perforated basket, it will ask for the diameter and rate of revolution. Now first, let us understand what is the perforated basket. So this is the perforated basket centrifuge. You will find a basket over here, and this is the perforated wall, and during the operation, a filter cloth is kept at the periphery of the inner wall. In other words, the inner wall is covered with the filter cloth. Slurry is kept inside the basket, and the basket is rotated with a high angular speed. And while operation, due to the centrifugal force, the liquid escapes through this basket because it escapes through the perforated basket as well as the filter cloth. So liquid portion escapes. But the solid particles, they cannot escape. They get arrested on that filter cloth and they make a thick cake on the filter cloth. So that operation is quite similar to, you might have seen inside the washing machine. To be very specific, the top loading washing machine. If you have seen inside the top loading washing machine, you will find a similar kind of basket where the clothes are put and water is also flown over there, and after washing, the basket rotates with a high speed and the water escapes, and the wet cloth, that means the cloth with some moisture in it, they are retained within that basket. So the same operation is done with the perforated basket centrifuge. Now this is the enclosure of that perforated basket centrifuge, and inside this enclosure this basket is kept, and this is a batch process, and it can be either underdriven or overdriven. It depends upon how the basket is driven. Obviously there will be a motor which will drive the basket or which will rotate the basket. So the motor may be at the bottom and basket may sit on the motor, or motor can be over that and basket can hang from the motor. So depending upon that arrangement, it is called underdriven or overdriven. This kind of centrifuge is very much active in pharmaceutical industries. And typical diameter of a perforated basket centrifuge will be having a diameter of 0.9 meter, a volume may be 0.085 meter cube, the perforations may be around 3 millimeter, and I have already said the cloth filter is there for smaller particles. And while starting, it may take up to 5 kilowatt, and once the inertia is obtained, then regular running wattage will come down to 2 kilowatt, and speed may go around 1000 RPM or so. Now let us go back to the simulation window. Here you can see the perforated basket configuration. You have to give the diameter, rate of revolution. So if you give over here, if you write 0.9 meter diameter and 1000 RPM, okay, so these two things you have to provide. Now we may find there is option for giving extra information about diameter and rate of revolution. Because here you can see the perforated basket centrifuge, Aspen Plus determines the mode of calculation, either simulation or design, by input specification as follows. Now, if you specify a single centrifuge, that uses in simulation mode. But if you specify multiple centrifuges, that means it is design mode. So, if you specify over here only one set of diameter and rate of revolution, that means you are using only one centrifuge. It is simulation mode. But if you use, say, another diameter, say 1 meter, it may be 1200 RPM or so. In that case, it is a multiple diameter and multiple rate of revolution operation. That means it is a design mode operation. Okay? And you have to specify this information, that is liquid surface, filter cake surface, and height. Now, all these information have to be given as a ratio of perforated basket dimension to radius. So, basically it is liquid surface by radius of the basket, or filter cake surface by the radius of the basket, or height by the radius of basket. So everything you have to give in terms of the ratio. Okay. And what is liquid surface? Liquid surface, suppose this is the basket, then this is the liquid height by the radius. So that is the ratio it is put over here. Similarly, filter cake surface, suppose this is the periphery of the inner wall and this is the filter cloth rather, and the cake has been formed like this. So this is the cake that has been formed after liquid has escaped the filter cloth. Then that filter cake surface by the radius, that is given over here. And these numbers are all default number that Aspen has given. Now you can change them or you can leave them for practice. If you have to work with the particular operation that is needed in your work area, then you have to give the correct information. Okay. The next thing is deliquoring model. There will be two types of deliquoring model. One is estimate residual moisture. That means you are asking Aspen Plus to estimate the residual moisture after the perforated basket operation is done. What will be the residual moisture inside the filter cake that can be estimated? Or you may want to specify the residual moisture, that I want the residual moisture to be like this, design the system on this basis. So that you have to provide. Okay. So that residual moisture you can give in wet basis or dry basis. Then the solid cake, you have to provide the information about filter cake medium resistance, porosity, and average sphericity. These three information you have to provide, and filter cake specific resistance and average diameter, these two things are optional. So basically this one and this one, these two things are optional. If you know the values, you can give, or if you do not know the values, you can leave them blank. Aspen Plus will calculate them based on other parameters that you have provided. Okay, so this is how the things work with the perforated basket. Then the next one is decanter type centrifuge. So this is a typical diagram of a decanter type centrifuge. Now this is the actual centrifuge and this is the schematic diagram. You can see the liquid feed that enters through this end and they are distributed over here, and the whole enclosure that rotates with high speed, axially rotates. And as this rotates like this, the liquid portion, it goes right hand side and the solid goes the left hand side, and this is the solid discharge point. Okay, and it is a continuous process. That means continuously the feed goes in, the liquid gets discharged, and solid gets discharged in this end. The rotation provides anywhere from 1000 to 4000 times of normal gravitational force. So the centrifugal force that is generated due to this rotation is around so much times of normal gravitational force. And it is very useful for water treatment, something like desludging, dewatering, etc. It may be horizontal, it may be vertical. Now let us see a YouTube video. It nicely shows through animation how this centrifuge works. The feed enters. Feed contains both solid and liquid, and somewhere in the middle the entire thing gets distributed. The screw goes forward and it pushes the solid, and liquid is going rightwards. Solid is getting discharged at this end. And there is an adjustable impeller, and this impeller controls the liquid level. And this liquid level is very important. Although we are saying it liquid level, but actually it is annular. The liquid level is annular. Okay? And this adjustable impeller controls that liquid level. So that's a decanter type. Now in decanter type, you have to give a classification model. There are 5 types of classification models that you can mention: ideal separation, ideal classification, square function classification, Stokes, and simplified Stokes. First, let us understand what is ideal separation. It is the simplest shortcut model that calculates the separation of solid and liquid components into their respective streams under assumption of ideal behavior. That means all the particles of the solid phase are completely intercepted into the solid stream, independent of their particle size of the solid or the solid density. That means all the solid particles will go to the solid stream. That is the ideal separation. Now, if you see the resulting separation grade efficiency, Tx is 1. Tx is 1 means 100%. That means 100% solid goes to the solid stream. So that is ideal separation. So this is the simplest shortcut model. On the other hand, the ideal classification, if you choose ideal classification, then an option for cut size is active for you. What is cut size? You know what is cut size? You have to specify this cut size. Suppose the cut size is D cut, then the resulting separation grade efficiency curve will be having this formula. The particles having size between 0 and D cut, this separation efficiency will be 100%, and the particles having higher than the cut size, they will not be separated. So here the cut size of 85 micron has been mentioned, which is over here. So dp above this cut size, it is 0, and dp below the cut size, it is 1. Okay, so that's how the grade efficiency is calculated. Okay, and then the next one is square function classification. In square function classification, you have to provide a boundary particle size, and this boundary particle size is denoted by d bound, and particles having size between 0 to d bound, its efficiency is calculated as dp by d bound whole square, and the particles having size higher than the boundary size is 0. So here the boundary particle size has been given as 70 micron. So below 70 micron, you have this formula, and you get a curve of this nature due to this squared function curve, and above this d bound it is 0. So that's how you get the separation grade efficiency using square function classification. Similarly, Stokes. Now, the moment you choose the decanter classification model as Stokes, the configuration tab is open, where you have to provide various information about the decanter configuration, like the drum diameter, the cylindrical length, the screw blade pitch. Screw blade pitch means you have seen the screw blade. These are the screw blade, okay? And pitch means the distance between them. So screw blade pitch and the rotary drum speed, the differential rotary speed, pond depth. So those information you have to provide. Now, why you need to provide them? Because for formulation of separation efficiency, two cases have to be considered. One is the solid field on the pond surface, and solids are evenly distributed over the pond depth. And for that, Tx, that is the separation grade efficiency, will be calculated. Here you will find various parameters like R cret, R neve, R dr. Now what is this R? R is the radius. So R dr means the radius of drum. R cret means the critical radius. R neve, if this is the periphery of the cylinder and this is the axis of that cylinder, then this is R neve. That means the distance between the axis and the pond surface. Pond means this one. This is called pond. So although we call it pond, but actually it is an annular pond because it is having a high angular velocity. So the pond is distributed over the full annulus. Okay, so it is an annular pond. So this is the height of that pond, or you can call it pond depth. So the distance between this axis and the pond surface, this is R neve, and this is the pond depth. So this is R neve and this is R drum. Now this red colored annulus is very important because this is the portion through which the liquid escapes. So ideally this R neve should always be greater than R cret. This is the critical. Now if the pond height, the pond surface goes beyond that level, that means the solid content which is suspended in this liquid, that will escape through the liquid outlet. They will not be arrested in the solid cake. That's what it means. Okay, so this is how R cret is calculated. You will have various other parameters like UC. What is UC? UC will be calculated over here. This is UC, that is the settling velocity as per Stokes' law, which will have the parameters like solid density, liquid viscosity, etc. And there is a centrifugal number C, which will have the rotary drum speed and angular acceleration also as their parameters. Okay, L pond is the pond depth. So if you add that L pond and R neve, then you will get the radius of the drum, which we have explained just now. So this is how Stokes' law based calculation of classification model is done. Now simplified Stokes' law is also given over here. You can read through it. So this is the simplified Stokes' law sedimentation. Now I am not explaining that, you can just read through it. Now deliquoring model. Deliquoring model, in case of decanter, you have various other things like stalls, Redeker, Stadager, Skubert, etc. So how the moisture content is defined in all those models, that has to be seen. Let us go to the help file once again. So this is the deliquoring models for decanting centrifuge. The main aim is to find the residual moisture. Okay, how the residual moisture is calculated by Aspen Plus. So that has been shown over here. Now this is the stalls model. Here you have to provide the stall model number phi1, which is a function of d neve, that is the diameter of, we have learned what is R neve, so it is d neve, so twice of that. The rotational speed and sine beta. What is beta? Beta is the cone angle, so this is the cone angle. Okay, and these are the dimensions that you have to provide: drum diameter, cylindrical length, cone angle, screw blade angle. Now the moment you choose stall, then all those information will be asked to you. Drum diameter, cylindrical length, screw blade pitch, cone angle. Okay, so cone angle, you have seen what is cone angle, screw blade pitch, rotary drum speed, etc. So all those things will be asked with the stalls model. Similarly, you have Stadler model, you have Redeker model, you have Schubert's model. In Schubert's model, you will find a function S. Okay, so this is a saturation function. And this saturation function uses epsilon, where epsilon is the cake porosity. So somewhere you have to provide the cake porosity also. So if you use Schubert model, you will see the saturation coefficient you have to provide, and here is the cake porosity. Okay, you have to specify cake porosity. The default value is 0.45, but you can provide your own. The Schubert saturation coefficient, this is the Schubert saturation coefficient N. N is used over here. So you have to provide this Schubert saturation coefficient and residual cake saturation. So all those information are required over here, so you can provide them and Aspen Plus will calculate them accordingly. And then next one is the disk type centrifuge. Now this is a schematic of a disk type centrifuge. It's a continuous process and its operation can be beautifully understood by a YouTube video where it has been explained with inclined and vertical test tube that how an inclined test tube is more efficient for sedimentation of solid than the vertical test tube. So let us go to see the YouTube video first. So this is a video by Tomo Engineering Company Limited. You can see for a gravitational force of attraction, it acts on both vertical and inclined tube. But for inclined tube, the sedimentation rate is faster than the vertical tube. Okay. For a vertical test tube, it takes a lot of time. For inclined test tube, it takes less time. And when these test tubes are inclined and they are rotated with a high speed, that is, if the high centrifugal force is applied on it, then what happens? You can see this is what happens due to the high centrifugal force. That's exactly the principle of the disk type centrifuge. Here you can see multiple conical disks are stacked in an enclosure and their gap, they are all inclined just like this. Feed enters through the top and it moves. So this is the slurry having both liquid and solid particles suspended in it. And they move like this and the entire enclosure, the disk, they rotate. Okay. As they rotate, the solid particles, due to the centrifugal force, they get accumulated at this end, and all the liquid portion, they go inwards and they are escaped through this end. Okay. This is the ball drive which rotates the ball. Now I will show you the animation through which you can understand how it operates. This is exactly how it operates. This is the rotating unit and these are the discs, and this disc rotates. This is the cross section of the disk type. The slurry enters from the top. They get distributed, and you can see the liquid phase, both light and heavy, they escape from the top, and how the liquid and solids are directed. So all the solids, they go and they gather at the solid outlet. The liquids, they go at the top. These are the solid discharge mechanism. And this is how the solid escapes from the system. So this is how the disk stack type centrifuge operates. Now here also you can find the ideal separation classification model, ideal classification model, square function classification, Skubert. You might remember in case of decanter, you had a Skubert delicurring model. Okay, but we are not looking for this one. We are looking for disk type classification where we have Skubert model. It's not delicurring model. Okay, and this Skubert disk classification model will be found from here. So this is the extended Skubert sedimentation model, where the separation is modeled like this. So you have to provide the separation sharpness, adjustment factor for channel inlet sedimentation, adjustment factor for channel sedimentation. You have to provide the configuration like outer disk radius, inner disk radius, number of disks. So outer disk radius means this is the outer disk radius and this is the inner disk radius. Okay, or this is the inner disk radius and this is the outer disk radius. And number of disks means this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe around 17 or 18 disks. And then height of channel, angle of disk, drum rotary speed. So height of channel means this is the height of channel, and the angle is this is the angle. Okay, this is the angle, or this probably. What else? Drum rotary speed. What is the angular speed of the drum? And all those information will be useful over here in calculating the model. You can see the separation sharpness. All of them will be useful for calculating the separation function Tu. So this is by Skubert model. Deliquoring model, we have to specify residual moisture for this classification. And the configuration I have already said. Now in the disk type centrifuge, the rotation provides around 6,000 to 12,000 times of the gravitational force. You will find this kind of centrifuge for the analytical lab use. It is useful for three-phase separation and useful in the pharmaceutical industry, food industry, and recycle industry. Finally, we come to the pusher type of centrifuge. The pusher type of centrifuge, it looks like this. Here we have two concentric perforated drum. Okay, and this perforated drum has been shown over here schematically. So this is one drum and this is another drum. The solid is fed like this. it is distributed. Periodically, the drum is pushed from this end to this end. Periodically, it is pushed. The solid escapes through this end, and the liquid escapes through this end. This is also a continuous process, and product is washed, and it is also useful for pharmaceutical industry. Again, I will show you a small YouTube video where you can see the animation and you can understand how it works. So overall, this is the pusher type of centrifuge. You can see the drum. So there are concentric drums, both of them rotate. The slurry comes from the top. They are distributed in the middle section, and the pusher pushes the solid material from one drum to another. And at the end, the solid is escaped. In the middle portion, you will find the water that is being used to wash the solid. And this is how the cleaning is done. And this is the cleaning process. The cleaning water is spread from the top, just as it is shown over there. So in the pusher, you will find the three types of classification model, which we have already explained. And it has deliquoring model. There are two types of deliquoring model, estimating the residual moisture. I mean, you can ask Aspen Plus to estimate the residual moisture, or you can use the plug and film flow model. So what is plug and film flow model? You can find in the help file. The moment you choose this plug and film flow model, the solid cake and configuration will be open for you. In the configuration, you have to provide the stage 1 drum diameter and drum length. So the perforated drum which you have seen, its diameter and length you have to provide. You have to provide the stroke length. I mean, for each stroke, what is the displacement the drum is experiencing, that is the stroke length. SIF, friction factor, product friction factor, you have to provide the rotary speed of the drum and push frequency. Okay, per minute or per hour, how many pushes are given in the pusher. So these are the configuration. Solid porosity and bulk flow resistance has to be given. And the saturation factor and saturation exponent. So this is the plug and film flow deliquoring model. Basically, you have to find the residual moisture which is the ratio of mass flow rate of liquid to the total mass flow rate. That is the liquid and solid mass flow rate combined. And here you have to calculate the residual moisture. By using this information, you need the liquid density, which is available from the property database. Epsilon is the porosity. You have to mention the porosity somewhere over here. And the S is the saturation. Okay. And saturation will be calculated over here. You will find A is the saturation factor and B is the saturation exponent, A and B. And the saturation factor and saturation exponent have to be given over here, and cake height also you need to mention. So this information you need to provide, and the pusher type of centrifuge can be simulated. Okay.